good. Thank you very much. It's my pleasure to be here, and thank you very much for all of you coming. This is a project that is very dear to my heart, and so I will share with you all the good and the bad and the ugly, as they say, because none of this, it's a research, but at the same time, the performance that we will put up on Friday requires really this stable, sort of debugged system, which is in some ways in contradiction to a research environment. So I have to constantly remind my collaborators, don't make any changes, no changes, because in this collaborative effort, students tend to constantly tune up things, and then the right hand doesn't know what the left hand did, so it's a real challenge. Any case, I'm going today, the lecture will be more a technical description of what the problems are, what we have accomplished, and I have a couple of videos what I will show you where we are at this point. So outline is information technology as a tool for interaction and collaboration, and how technology is influencing art dance as an example. We took dance as a way of testing this physical interaction in a cyberspace. That's really what it is. And then I have a couple of slides, kind of more philosophical slides, how artists challenge the technology, and you will hear more about that on Friday from my collaborators, Lisa Weimer and Catherine Mesur. So the next few slides, we shall explain the technical details of the tele-immersion system. So what is tele-immersion? Tele-immersion is an emerging technology that enables cooperative interaction between geographically distributed sites. This is achieved through realistic reconstruction of the scenes in virtual space in real time. So now, you know, what are the applications? Well, there are many, and there is a list of them. And but I think I found Professor Narstedt from Illinois sent me a very nice advertisement that what the current sort of tele-immersion is. And in fact, there are two companies that you are probably familiar that are making, in fact, money out of this tele-immersive technology. In fact, it's more teleconferencing rather than tele-immersion capability. And I will try to impress upon you what the difficulty and the difference is. Nevertheless, Cisco and Hewlett-Packard are in this business, and they are apparently making good money out of systems. So, but please notice that the main thing in these images are the displays, you know, where they have four or six displays, where they can track as you are talking. It's basically a fancy teleconferencing system where they can track who is talking, and the displays are changing as you are moving around. My main objective of this slide is, besides showing you what the current technology is, that they also have local displays, so local classrooms, situations. But notice here with this car, this is one of the applications of tele-immersion application, and that is that you can digitize three-dimensional objects that you want to advertise. And unlike in here, where you have people and then on a separate screen you have the three-dimensional object, with the technology that I will show you, we can do it in much more natural way in one display, so that people can really feel that they are there. That's sort of, although I will show you where the issues are. So what is teleimmersion is really a kind of a connectivity using standard network, and that is one of the challenges between different sites. So this is Berkeley, that's University of Illinois, and that's my former university, Penn. But right now, what you will see on Friday is just this bidirectional connection between Illinois and Berkeley. Why, you can ask, why has this technology hasn't really materialized? Why is it not broader acceptance and dispersion? And the reason for that, in my opinion, is that it really a convolution of at least 4 different technologies. And unfortunately, as in academia this typically is, we live in various silos. So you have the image processing group, you know, which is doing the data acquisition. Then you have the reconstruction, that's image, but hopefully one can combine that with image processing. Then you have the 3D display, which is the graphics community, which is unfortunately different from the image processing. And then you have the networking people who sit completely different room, okay? Now, so when I came here, I really came here to really fulfill the promise of the CITRIS, which is the Center of Information Technology in service to society. And if you really want to do that, you really have to be necessarily an integrator and an interdisciplinary person, which is a challenge in academia, I should say, and I'm sure some of my colleagues around here are knocking their heads and they understand how it is. So for example, at Berkeley, there is a vision seminar on Tuesday, there is a graphics seminar on Thursday, and I actually don't participate in a networking seminar. But in some ways, if you really want to be an integrator, you should be in all of these seminars because you really want to bring all these, at least subset of these people together. Anyway, so how we do the image reconstruction is we are using 3 black and white cameras. Now, you know, you have 2 eyes, and so that's how you deal with the reconstruction of the depths, which you lose otherwise with 1 eye because of the 2-dimensional projection of the 3-dimensional world. And I, from a long time, because I have been doing work in robotics, I always felt that vision is losing something by not considering the 3rd dimension. And there is plenty of work going on with doing just images from the web and doing analysis on them, and that's very interesting and important, but I am interested in really 3-dimensional recovery of 3-dimensional information. Now, why do we use 3 cameras as opposed to 2 cameras? Because we really are interested in reliability, which is another thing that in academia is an iffy problem, because reliability is, in academia, you are more interested in novelty rather than robustness and reliability. On the other hand, if you really want to make systems useful, as CITRIS is sort of taking as its own agenda, then you better make systems that will be reliable and robust. Otherwise, people are not going to use it. Nobody wants, you know, the folks out there are not interested how many papers you have written, but whether the thing that you develop will work. So reliability. So the reason we have these 3 cameras, because we are computing correlation between pairwise, the left and the middle, and then we, since we have 2 independent measurements or reconstructions, we can combine them or make some decision making whether we believe the data or not. And you will see some problems. So these slides are from Gregory Kerela, that I have to acknowledge, who has been really doing a remarkable job on the fourth floor, and he has really tested and debugged a great deal of the system. So what do we have? What we have is a 360 degrees capture capability. And unlike the capture systems, which use various reflectant markers on the body, from the very beginning, we wanted to have a system where it's totally unobtrusive, in a sense that we take images and the people who are in the system don't wear anything, so they just act very normally. We do full body 3D reconstruction, and we try to do it as real time as we can. At this point, we capture images, I think it's 24 frames per second, but unfortunately the reconstruction slows us down to roughly half, so about 12 to 14 frames per second. And then, of course, the transmission is another bottleneck where we get slowed down. So we are not able at this point to deal with very fast motions, but real time really questions the existing vision algorithms. Let me tell you that it's fascinating. You know, you have all these publications, you know, tons of it, you know, about reconstruction and tracking and motion recovery. But if you are asking what can you do in real time, you really have to re-examine every step, because you really have to worry about how many computations you absolutely have to do and what should they be. So for example, you want to replace square root, you know, by some differentiation and details of this kind in order to really squeeze out of the algorithms as best as you can. So this is the lab on the fourth floor, and we have here the cameras, as you see. These are what we call a cluster. We have 3 black and white and 1 for color for rendering, and these are the views that we had. I believe we have changed them a little bit. And this is the configuration that you can see of 3 black and white, and then top the color. Okay, so the system, we have 48 cameras. Now, please understand why I'm so nervous about the Friday performance. I have to make sure that 48 cameras work, 13 computers work, 4 different networking switches will work on our side. Furthermore, in Illinois, they have 16 cameras to work, 6 computers to work, and I don't know how many switches they have, you know, in order to make this work. So, I mean, you know, believe me, I wake up in the middle of the night and pray. I mean, what else can I do? I mean, all right. So this is the algorithm that we do image capture. Then we resize the images, unfortunately, and I think after December 8th, we are going to re-examine this whole thing so that we can have a higher resolution. Because the reason we resize it is, again, the real time. You know, there are 2 ways how you can increase the speed. One is that you reduce the data, okay, and this is part of that. And the other one is that you try to parallelize, but not everything can be parallelized. So we resize, then we do rectification, because the cameras are not straight this way, so they are tilted, and therefore we have to rectify them into this position in software. Then we do background subtraction. Again, background subtraction, the reason for that is that we want to reduce the amount of data on which we do the reconstruction. So we just want to focus on the humans. And then we do edge extraction, and then we do region-based. And here you have how long it takes, 30 milliseconds, 20 milliseconds. So we really pay attention to timing and the quality, because that's what really is. And then we have reconstruction, so total 130, 180 milliseconds it takes the computation. So here is the image capture and resize. This is Sang Hawk, who really started the lab about 4 years ago with me. And then this is the background subtraction. You get the human. As you can see, it's a binary image. Black is the background, and the white is the stuff that you want to do the reconstruction. Here are the edges. And then here is the depth map. And notice that you have some holes, and this is where we couldn't find the correlation, okay? And that's one of the life stories that I will continue telling you, okay? So the real life problems, and this is really from Greg. So first of all, we have holes and noise, okay? We have calibration error. You will hear me, calibration, 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 ad infinitum. So then we have some missing data on, on the occlusions. Sometimes the cameras, we have 48 cameras, but the cameras don't see every concavity. So if the camera doesn't see it, we don't have the data. All right? I mean, the only thing we could do is maybe interpolate, but that costs you time. So we don't do that. And then poor blending of the pixels. So these are all the real problems. So headaches, cameras producing a lot of noise, outliers, poor reconstruction, holes and flickering, and you will see that in our video. Small range of capturing, namely range in depths. What is the resolution of depths we can get? I mean, there is a limit. Some cameras do not work always properly. We have to re-examine and, as I said, do the calibration. And then delays in data transfer. I mean, the networks have delays. I mean, that's fact of life, that especially when you talk about long distance. Okay, so we have tried, and in fact, it's Gregory and Brad Wilson and the other students who work with me. We have examined every step as we went along. So configuration of stereo clusters. We looked at the volume coverage analysis and camera configuration analysis. We rearranged the cameras to increase the coverage, and we are solving some existing problems. And then I will show you. So here we developed a simulator where these are the cameras where they are. And so this is strictly geometry. It's not really anything very profound, but you want to understand if you move cameras, you know what the consequence of and what is the volume where the dancers can dance. And so now we have this, and actually this will be very useful once one of our hopes is that we can make this system portable, so that we can take a mini tele-immersion to some other place and set it up. And depending on what you want to, where you want to focus your camera resolution, this simulator will help us. So for example, sometimes the application may be such that you really don't need to see the legs, only half of the body, but with the higher resolution that we have now. Now we are compromised because we really need to capture the whole body. So if you really want to, for example, for training purposes of mechanical systems of surgery, for example, you want to have a more intensity of resolution on the hands of the surgeons, and so you want to put your resources, this really a resource allocation, on more the face and the hand. Okay, so here is the camera simulator. So this is what we can reconstruct from, and you can get what, you know, the output from the simulator, what you really can capture, and from which angle. So sometimes maybe you don't need, we have a 360 degree, maybe some applications you don't need the back. Okay, in our dancing application, the back was rather important. But if you just want to frontal, then maybe 180 degrees will suffice. So again, you really want to understand that. Then you have to think about it, what kind of lenses are you going to use? Narrow lenses will give you more focused resolution. Wider lenses will give you a better coverage. So you really need to worry about these things, and here is an example. A narrow lens, 6 millimeter, gives you a narrow view. You see much better the shirt, the texture, while the 4 millimeter lens gives you a wider view. I mean, this is optics 001. Nevertheless, you know, when you make it as a part of the system, you have to think. I'm trying to impress upon you that you really need to think about every step as you go along. Okay, so this is this is an example of the camera arrangement. Then you need to worry about illumination. Okay, what kind of lights are you going to put up? And so photometric properties of objects. Well, typically in computer vision, people talk about Lambertian surfaces. They sort of assume that Lambertian surface is such that from every angle you will get the same light reflected. Well, that's illusion. I mean, there is in reality no such. I mean, you really have to paint things very carefully, and in the lab, yes, but in the real world, you have highlights, you have mirror type of reflections, metallic objects, plastic objects, okay? So you in order to deal with, so you have reflective mirror and specular objects. So specular lights create problem with 3 dimension because, in fact, it gives you a very high contrast, but it moves with the camera, the highlights, you see? So if you use that for your correlation, you get the wrong matches. So this is well known in computer vision, but we had to worry about it. So we had to install diffusive light needed to prevent shadows. So here is an example of the things that you play with, too bright, too dark, and somewhere in between. Just as to show you that, you know, what we really need to worry about. Okay, so here is our lighting. We have diffusers, and these are the data that we had to deal with. Okay, so now the other thing we had to deal with our dancers, what should they wear? Which clothes will show better, okay? So they were very kind, and that's where you really need a true collaboration and friendship with your collaborators, because, you know, we needed 2x, so I will show you. So here are some examples. They brought all kinds of T-shirts and materials to test, you know, what will be the best colors and still aesthetically pleasing. And I think they settled on this color, on this blue. And I also was ordered to dress in some light colors for Friday. So, okay, so camera calibration. Camera calibration has been around, ladies and gentlemen, since I was at Stanford, which was in 1969. Erwin Sobel did his PhD thesis on camera calibration. And you wouldn't believe it, but it's still a problem. And the problem is that mathematically it's a well understood problem, okay? But here is the issue. If you have more than 2 cameras or 4 cameras, then the errors compound. And then the problem gets non-trivial. So scalability in this business really hits you into your face. And so pinhole perspective, so there are assumptions on this calibration, and we have settled on 2-step calibration. I mean, there has been always 2-step calibration. One is the intrinsic parameters, which are the focal lengths, the difference in CCD chips. You know, the pixels are actually not squared. They are rectangles. So you have to find what is the ratio of these pixels, what is their separation. Okay, you really need to calibrate. Then the center of the CCD chip you have to find through calibration. So those are the intrinsic parameters. And then you have the extrinsic parameters, which is the camera position. It's rotation and translation. As you move or it moves. So it's a relative motion. Okay, so it really turns into a nonlinear optimization. And as you see, there are toolboxes, and here is luckily it's a linear system, so it can be made, at least the computation can be made relatively fast, but you need to take a lot of data. And since we have these 48 cameras, so you need to take them from every possible angle so that you can calibrate all the 48 cameras. And that is the challenge. So then also we have radial distortions, namely you have this blurring, and that's due to the lenses, lens curvatures of the lenses. So we have to correct for that. So then you have errors. So what kind of errors do we face? So here are depth errors to lens distortion, depth error due to non-parallel CCD to the lens. You see, you would assume, and in normal applications, you can assume that the chip is parallel with the lens plane. Well, but small changes, you know, cause you. Remember, we are building an instrument, and physicists know how much you have to spend if you really want to believe in your measurement, how much you have to worry about calibration. And this is really what we have to do. So there are depth errors due to non-parallel CCD, and these errors, depending on the distance, will increase. Depth error due to composition of calibration error, position and rotation. This is sort of mutual positions between these clusters. Also add, you know, the errors. Okay, so discrete calibration is very time-consuming, and yeah, I don't know. Gregory is here, I hope, so he can tell you how often do you calibrate, like every 2 days or 3 days or something like that. Anyway, accuracy of the entire system depends on calibration of one camera, because you have one kind of master that you make it as a 0, 0, and then you relate everything else with respect to that as a coordinate, as a 0, 0 coordinate system. We use LEDs because they are for the extrinsic parameters, because they are points that you can see from any angle. So that's the value of the LED points. And okay, so that's sort of about the reconstruction and the data acquisition. Now, what are the problems with networking? So I am not a networking person, but I collaborate with a networking person who happens to sit in the University of Illinois. So here are the issues. Ability to send captured data through network in real time with minimum delays. So again, you know, the supercomputing people have done experiments in this, and so does HP and Cisco. They do this fancy video conferencing on a private cable network. so that you have no switches in between, and therefore you have full control of this networking problem. Now, I promised to the National Science Foundation that we are going to develop a system for everybody, so that anybody who has access to internet can use this technology. So we have to deal with all the real problems. So we have a problem of reliable transfer of three-dimensional data. We are accumulating enormous in gigabit size of data, so we really have to worry about, how we do the compression, for example. Okay, so we have the data. So how the data is being represented is in this, these are bytes, okay? So we have a header which has 10 bytes and depths 2 bytes, and the color, each color has 1 byte. So this is the size per point, okay? And then we have the header is composed of a frame number, which frame you have, and then how we can compress it. So that is, so we are using some lossless compression, but of course that is not good enough, because we are using gigabit network. Nevertheless, the gigabit network is shared. So in reality, we have only 100 megabit throughput. And of course, our data is much bigger. So that is another challenge. So we have, together with our collaborators in Illinois, we have looked at, what are the advantages of a 3D. And we have been challenged by our reviewers and everybody else. Why just not 2D? Why just don't you send different views of the 2D? And one of the arguments for that is that you can view the 3D. If you have the 3D, you can view it from any angle. So you, as a user, have a control which view you want to see. That's really the value. So that's really at your will. That's really the value. Now, there is another value which is not on this, and that is that if you have a 3D data set, it's much easier to combine, to integrate different 3D data sets. So, for example, if you have a scientific data set, or you have a medical MRI data set. What happened? Oh. Was that, pardon me?
Frequency interference.
Oh, frequency interference. Okay, all right. So now we have looked at what is the transfer speed during 1 minute trial, and this is the average for different clusters. And you can see different clusters work harder, because if you are a cluster, you look at you from the front, you have many more pixels to work on than if you are a cluster that looks at you from the side. So you see the cluster 8 is not working as hard as, for example, the cluster 4 and so. So we have looked at the network relatively. So the transfer speed, this data shows that the average data transfer speed is between 100 to 200 kilobytes. The highest average transfer speed is for data coming from the cluster 4 and 10, which capture the front, as I mentioned. And backside of the trunk, the results show small, I somehow, I lost some, yeah, as you can see, packets got lost. Good example. A standard deviation among the 3 trials of similar experiment. The maximum data transfer observed during the experiment was 400 kilobytes. Okay, so networking problem. So the current problem, each camera has to send data to multiple renderers. because, you know, in Illinois, they are viewing what's happening. We are viewing, and in fact, for the Friday, we will have 2 renderers. One will be in the lab so that people can see what they are doing, and the other one will be in the lobby. So we have multiple renderers, and of course the reliability of connection, reliability of transfer speed. So, you know, in order to deal with this networking issue, one of the things that I took upon ourselves together with Ji-Ming Lin, who is somewhere here, was that we started to look at it, how we can compress the data in a dramatic fashion. And so the problem of compressing tele-immersion data via skeleton, so we said, okay, if we can extract skeleton, you know, just your bone structure, so to speak, and then let's say we send the first complete data to Illinois, but then let's say the subsequent 10 frames, we will send only the skeleton, all right? And then reconstruct, you know, based on the first frame, and then upgrade it, let's say, every 10 or so. We will clearly very much save in the transmission data, but question is how much will we lose, okay, in terms of veritability of the performance. And of course, it very much depends how fast people will move. I mean, if they move relatively slowly, then 10 frames of skeleton will not be very much damaged. So I'm sure this whole thing will require much more testing, but this is sort of the idea. So Ji-Ming has developed a data compression algorithm which had to, and the challenge was how to again make it fast so that you can extract skeletons in real time, which has been the challenge. So he developed this an algorithm. So here is so the first thing we do is when you come to the lab, we image you, and we ask you to do few basic exercises so that we can detect different joints, all right? And we do this offline. So the first skeleton fitting is done offline, not real time. But then once we have that, then all the updating is done in real time. So the segmentation in some ways has to be done, at least for now, offline. So what you see here is a segmented body, as you can see with these different colors that we got. And this is another, this was Sang Hog, did some similar work in segmentation. Okay, so this is our experiment, which we did rather recently. What was it, like 2 weeks ago? Yeah. And this is Mr. Gosch, Robert Gosch, who is a senior citizen and who is collaborating with us in our other project for elderly. But he's also a teacher of Tai Chi. And so we are running an experiment of that if you see a teacher, and this can be pre-recorded, which is, and you show students this versus just a video, could they learn faster the movements of Tai Chi than with just video? And we capture them, how they do that, and we can superimpose how accurately they have learned it, and thereby get quantitative measure of this, how well the 3D, where the 3D makes a difference versus the 2D. That's really the question. But in the meantime, Ji-Ming took it as a good experimental data for his compression. So, excuse me, I'm not sure I remember all the details, so I need to remind myself. Okay, here we go. So the left image, and I will play it again, is without any compression. And then this is with 15% jimming.
It's full compression.
This is
the quality of that noise too bad.
this one. And this is just the skeleton, and then dragged the data. So you will see that. So let me go back and show you again. Right. Okay, so you can see that actually this, I don't know if you can see. The skeleton, there are some differences between the original and the skeleton compression, but unfortunately I fear that this was not very bright enough so that I cannot really make the good case. But as I look at it on my screen, and later on you can see it yourself, while originally you see those white errors, dots, so those white error dots disappeared in the reconstructed. So in some ways, the reconstruction and the compression does a certain filtering, which is not as surprising as one would otherwise. So now I have two more slides on sort of the philosophical question, and then I will show you the dancers. Oh, sorry. So let me just show you maybe the dancers so that we can then talk about this was recorded, when was this, 2 days ago, or one, pardon me? A month ago, okay. All right. Let's see. Uno momento, I will be, okay, my computer here, okay, and I guess this would be it, I hope. No? Huh?
Yeah.
Pardon me?
It doesn't seem like the CD is loading.
Oh.
If you go up again, it should hopefully be there.
Where?
That's right, the back button.
Yeah. Well, it should be here. Yeah, here.
Should I bring my laptop? We use my laptop. I can bring my laptop.
Okay, all right.
It doesn't eject the CD.
Just the CD, that's what it is. Okay. All right, so while you are bringing your laptop, why don't I just show the last two slides, and then I can play, the CD. So one of the questions that the dancers are asking is summarized on this slide. What is real and physical? So one thing that you will not see on the video, but you will see it on Friday, that when they dance at Berkeley, on the screen, they see the other dancer and they might be hugging and so. But in reality, they're in air. Okay, there is nobody there. All right, because the other person is on the other side. So there is an interesting psychological question that I would love to have a psychologist to address. Namely, there is a conflict between what your visual sensors are telling you and what your kinematic sensors and tactile sensors are telling you. And what does it mean? I mean, how does that influences their feelings and so forth? So that's the real question. What is real and virtual? There seems to be some ecology between these two states, though ecology doesn't necessarily mean harmony. So artists have been worrying about this. And indeed, you know, how we can incorporate or deal with this virtual versus real world, and where it plays a role or where it shouldn't play a role. So, for example, in our Friday demonstration, we are going to show you first this, hopefully when everything works, the dancers in Illinois and Berkeley dancing together in the cyberspace, and you will see that. Then the dancers will come down and will dance in real. You will see them flesh and blood dancing. And then we will show you just dancers from the lab locally, okay? So that you can see what the difference between the networked communication is versus a local way of, it just will be piped from the fourth floor to the lobby, so that you see the display without delays and all the stuff, that the networking stuff. But as I said, that is really the issue. Okay, so I think I am ending here, and so let me just play you. It's 2 minutes. So do you have it? And then we can open for discussion.
Is this the CD? Or?
No. The CD is here.
Okay, she's going to bring a paper for me. It's locked
How can it be locked?
from the software.
Oh, from the software.
Excuse me.
It's good to have technical people. Yes. Okay. Oh, okay. Yeah, all right. So he's playing it, so it's okay. Oh. Okay, good. All right, so this is Lisa Weimer, and she's a professor of dance. And this is Renata Shepard from Illinois. And this was captured here. Renata came to rehearse with us from Illinois and Berkeley. But you can see all the problems with the holes, with the extra dots, and all that. But this is real time. This is not really anything, you know, no editing, no special tricks of any kind. This is what we have. They were very interested in this notion that you can come in and out from the cyberspace. Oh, so this is Mr. Gotch with his Tai Chi. I think you saw that, so I think we don't have to show that again. Pardon me? Oh, yeah. Oh, I see. Okay, good. Yeah, okay. see the value here, and again, we have to prove it psychologically, that the three-dimensional, the fact that you can really, as you would be able to move around, has a value. So hopefully you will see similar dancing from, you see she's coming in and out. You will see similar things remotely. Actually, I felt very apologetic about, you know, all the noise and everything else from the technical point of view, and was fascinating because the artist saying that this is pretty, that you know, so it's all in the beholder's eye, you know, how you view it, but I still would like to give them the option of having a more perfected image than you know. Okay. All right. Thank you very much.
Very good. Of course, we have time for a few questions, and actually, I have a quick question. Do you really need a psychologist to tell me whether dancing with a real woman or an imaginary one is better? I don't think you need to hire a psychologist.
No.
Hugging Ruzena right now is much better than hugging any image.
But then again, you know, what I am interested in is to understand. Okay, I grant you, sure,
thank you.
Sure. But you
I'm
know,
glad my blood still runs in my veins.
But considering that we have all this pain in traveling on the airports and going to various meetings and so forth, what are the applications where we can get by with this kind of technology? Okay, where it's very suffice. Okay, I am not. Today's person, I'm yesterday person, so I'm not going to sell it that it will cure all our problems. But the question is, where is this technology appropriate? And from the artistic point of view, the artists are using this new media for creativity and for, I mean, they always have been expanding their horizon. And this is a new technology especially suitable for physical movement. And the question is, how can they... Dance is a communication. It's a non-verbal communication, okay? So the question is, what kind of messages can we deliver better in combination with this technology than without? That is what I am interested in.
Very good. Another question from the floor? Yes, Dan. Do you need a microphone for that? Oh, sorry, you do. I'm very close.
So you did a great job of explaining what you do from the sending end. You have lots of cameras, it's delightful compression.
Right.
Help me understand what you see of the UIUC data. Is it a big screen like we're seeing here? Is it some kind of a display that changes as I change my position? Or is it just a 2D view that we're seeing on our side of their data?
Oh.
We'll see it on Friday, I'm sure, but give us a sense of what we're seeing.
So right now, okay, they have only coverage of 180 degrees. So what you could see, and Gregory designed a automated 3D mouse. I mean, we have a 3D mouse that you can pick any view you want to, okay? But for the performance, we didn't want to futz around with mouse. So he designed that you can go sort of around. Now with the UC data, unfortunately, you know, we don't have the back. So the only thing you will be able to see is, you know, 180-degree different views. But let me tell you, there is another thing that I didn't talk at all about, and that again brings us back to a calibration. That, you know, the UC data may show you as a 6-foot person. The Berkeley data will show you as a 5-foot person, so we need to calibrate this integrated size of people and where they are and their relative position, because while they may be doing this, on the other side, it may look, that they are going through the person. So the integrative calibration, again, is important. And right now we are doing it by hand, but that's the next thing, yeah.
Professor Goldberg.
Ruzena.
Yeah.
So this is interesting because I love this comment that the artists love the
Yes.
the imperfections,
Right.
and I kind of have a sense for why that is, because they are, I mean, those artifacts.
Yes.
There's something fascinating about those because you haven't really seen those before, and I think those point to the process. That's something really new.
Yes.
I mean, dance is so old, and it's such a.
That's right. That's right.
But this is a way of looking at dance that we've never seen before. I mean, one of the aspects that you're getting at is that you can move around 360
yes,
degrees.
that's exactly what
And
I'm.
dance is still performed the old way, where there's a stage and there's an
Well,
audience behind.
when they practice, they have mirrors,
Right, for them.
as you know, for the same reason, because they want to see themselves from different angles, and this enables them to examine them, all around.
But one of the things that's so interesting about using dance as a subject is it's all about creating illusion. And all theater and all actors are always creating illusions. When they're doing acting, they're actually seeing something completely different. They're seeing
Yeah.
stage lights and markings on the floors, and they're ignoring all that and creating this illusion for us that we then can believe.
Yeah.
And what's interesting here is that you're actually you're dismantling that illusion to some degree.
I don't
And-
think you're disagreeing. I think
No, we're agreeing.
Yeah.
perception of
Look, I am an
Yeah.
engineer, and I will not pretend anything
See,
else.
that's the engineering view. It's the art.
And
Okay.
but
Final question from the floor.
I enjoy the interaction with the artists because they pose questions that I would never dream about. I'm worried about the perfection of the technology.
This is one of the wonders of CITRIS, that we can have both
Yes.
artists and engineers in the room. Is there one final burning question before we close? Yes. I should give you the conch for a second.
I noticed in the dance here that the dancers put their arms around one
Yes.
another, so the arm is in front of the second dancer.
Yes,
Presumably, one of them is going to be in Illinois and one's going to be here.
that's right. That's
So
right.
do you show that blocking of the person behind in your software?
Yes, it is. Yeah, that's part of the rendering part, which I didn't talk about, which is the graphics, which displays all the pixels that are in front of rather than that are behind. Yeah.
Very good.
Okay.
Well, final round of applause then.
Thank you.